will talk about different noise models. In the previous video, I had given an introduction for what is an additive noise. So in the process of image degradation, you will have a degradation function, then you will have an additive noise. The more we know about the degradation function and the additive noise, we can make the estimated image after restoration look similar to the input image. Okay, so it is important to know the behavior or the nature of this noise function or eta of xy. So we will discuss in this video about different noise models. So before we go to the discussion on noise models, I will just give an introduction about the different terminologies or different aspects that we will talk in the coming section. So imagine that I have a vector, let's say x equal to some value. Let's say I have all the values 5, 5, 5, 5 and 5. Okay, I have 5 values. Now what I'm trying to do is, if I plot the histogram of this particular x, then you can see that we'll have 0 value here, 1, 2, 3, 4 and 5, and this 5 will get a count of 6. So if this is my y-axis, okay, if this is my y-axis, I will get a count value here equal to 6 because we have 6 5s and all other values are 0. Then I don't have any value for 6 or 7 after this one. Now suppose that I'm initializing another vector, let's say n is equal to, I'm adding some values, I'm giving some values, suppose that I'm giving -1, 0, 0, 1, -1 and 1. Okay. Now if I plot the histogram of this particular graph, or if I just plot the histogram of this n, then you can see that the graph will look like this. Then this is my 0 point, and this is 1, and this is -1. Then I have 2 zeros here, that is 2 zeros, and I have 2 ones here, then I have 2 ones and 2 -1. So this is the point 2, and I have a point 1 here. So we have 2 -1s, 2 zeros and 2 ones. Now imagine that I am finding a new vector. Suppose that I am finding a new vector. Suppose that I am finding a new vector called x plus n. Then x plus n will be 4, because we are adding element by element. 4, 5, 5, 6, 4 and 6. Okay. Now if you plot the histogram of this vector x plus n again, then you can see that this is 0, 1, 2, 3, 4, 5 and 6. So I have 2 5s and I have 2 6, then I have 2 4s. Okay, so all these counts are 2. So what actually happened? So I just had only one pixel in this original vector x. Then this is the noise that we are going to add. Let's suppose that I'm calling this n as the noise, and this is a histogram of the noise that we are going to add, and this is the final image, that's the final vector that we are getting. So in this case, the original vector, original signal is distorted by noise. Then we can see that this is the histogram of the signal with noise. So if you see that there is some kind of information underlying in this noisy vector, that all these values are kind of equal, which means that this particular signal x or the particular vector x can be distorted by a noise where we have a histogram of equal numbers for each values. Okay, so this is a basic idea that we are going to see and then we will be just talking about what is this, what are different kind of noise model. So I can call this as a noise model because this is actually describing what can be what can be different values of the noises in the noise signal, and what can be different counts for each specific value for the noise signal. Okay. I will just quickly show a MATLAB example here. Suppose that I have x equal to I'm taking a vector of size ones of 1 comma 10,000 into let's say I'm taking a value 25. So you can see that if I plot the histogram of this x with 1000 different bins, you can see that uh, this histogram has only one value, that is the value 25. Okay, I will just plot it for 100 bins. So this is just showing you the value of the signal 25, and we have 25 values with 1000 counts. Okay, now I'm initializing another vector. Let's say n is equal to I'm using a function rand n, but that will be giving us the giving us a random number, and suppose that I'm getting a random number vector of size 1 by 10,000. Then if I plot the histogram of this noise for 100 bins, then you can see that this is the histogram, that is we have zero values, that is if the most of the values in this particular vector n will be closely zero, then we have some higher values and some lower values, but the values of higher values which are equal to 2 or 3, or which are equal to -2 or -3, the counts are very less. Okay, and we have most of the numbers in the random number n, which is mostly distributed in and around the value 0, that is between -1 and 1. Now look at what happens if I add, I'm creating a vector, let's say sum, or xn equal to x plus n. This is a new vector I'm forming. Then if I plot the histogram of this xn and for 100 bins, so you can see that we previously had a value 25 at the center, but most of the values 25 are now distorted with the noise function or noise signal, where the noise values were mostly 0, and it has some values going maximum up to 3 and minimum up to -3. So if you add those values with 25, then the 25 value is actually distorted with the noise. Okay, now this is actually, if you plot the histogram of n, if you plot the histogram of n, then this is actually a noise model. This describes what are the most probable values of the noise in that particular noise signal. So here it is actually 0 most of the time, the values are 0, and a higher contribution values are between -1 and -1, and we have values greater than 1 and going maximum up to 4 or minimum up to -4, but the count is bit less. Now what we will do is, in noise models we will be describing, instead of numbers we will be describing those in the terms of probability densities. That is, what is the probability that a value could be 0 in my noise signal is, will have the highest probability in this particular noise model or noise signal. Okay, so the first kind of noise model is the Gaussian noise. Gaussian noise will take this form, that is we will have a mean value, that is the most probable value, or it will have the highest probability. And here in the x-axis we are actually describing the parameter z, that is the value of the noise, and the y-axis we are describing p of z, that is the probability that a value is equal to z. And this is the function by which we can generate the noise p of z, or the probability density function p of z is equal to 1 by square root of 2 pi sigma e raised to minus z bar whole square divided by 2 sigma square. Here z bar is the mean value and sigma is the standard deviation, or SD, and sigma square is the variance. Okay, so whenever we have a noise signal like this, or whenever we have a noise model like this, and if we can determine its exact function or the probability density function, then that will help us to understand, help us for the image restoration process. Okay, Rayleigh noise has got the probability density function of this form. That is, the values is actually starting from a point A, and the highest probable value is a plus square root of b by 2, and it has got a probability 0.607 square root of 2 by b. And this is the function that is given for Rayleigh noise, and this is the value of mean as well as the variance. Actually, if standard deviation is sigma, then variance is sigma square. So this is the value of mean, and this is the value of variance. So this is the function for Rayleigh noise. Next we have the Erlang noise or the gamma noise. So gamma noise actually start from a point 0, and this is the function given for the gamma noise. That is, it is given by a raised to b, z raised to b minus 1 divided by b minus 1 factorial e raised to minus az for the value z greater than 0. So this function starts from z, and this is 0 for every value z is z less than 0. And in this case you can see that the function actually starts from z greater than or equal to a, and this is actually 0 for z value less than a. Then we have the exponential noise. So for exponential noise, we have a case where we have the highest value that is equal to this 0 value, then the contribution of all other values are decreasing exponentially to the right side. Okay, and the mean is given by 1 by a, and standard deviation is given by 1 by square root of a, and the function actually starts from for every value z greater than or equal to 0. Next one, and one of the important one, is the uniform noise. The uniform noise is the values will be starting from a and it will be ending at b. So the function is only defined for the values, or the noise is actually non-zero for the values between a and b, and all these value has got equal probability. That is why this is called a uniform noise signal. So the value is actually 1 by b minus a, and the width is actually b minus a. So any value between a and b has got the equal probability. So if there is a 1, for example, if I have a value here, let's say 2, and I have a value here, let's say 3, and this will be 2.5. So there will be an equal amount of 2 values, equal amount of 2.5 values, and equal amount of 3 values in the entire noise signal. And this is the mean value that is given, and this is the variance. Mean value will be the center value of this a and b, which is given as a plus b by 2. Next one is another important noise signal, that is the impulse noise or the salt and pepper noise. So in this one, impulse noise, we have only two different values. Just take this image down. Okay, I have only two different values. One is a, another one is b. So there is no noise between any value between a and b. So probability of a is given as pa, and probability of b is given as pb. And this is no more a continuous function. It is just it is having two distinct value of a and b, and the corresponding probabilities are p and pb. And this is actually called a salt and pepper noise. For example, if you have a noise where all the values are either 0 or the maximum value, let's say 255, then we will have some probability for having the value 0 and some probability for having the value 255. This is called the salt and pepper noise, whether the distortion will be only with having a black pixel added, or it will be having a white pixel added. Okay, so in this, if a image has a salt and pepper noise, the median filter can be used to reduce the noise in the spatial filtering domain. Now, I will quickly show you a MATLAB example how the noise models of a distorted image or the histogram of a distorted image will look like. Suppose that I have an image im and I will show the image using image show. So this is an image that I'm going to demonstrate as an example. Here we have three different intensities. We have a completely black region and a gray region and a white region. And if I plot the histogram of this image, and you can see that we have three different intensity levels contributing as the majority of the pixel values. So we have 0 and we have say A level, and we have a white level somewhere around to 25 or something. Now I have another image, let's say I'm calling it as capital I. Capital I is an image, and you can see the image capital I. So this image is the same image that we have seen previously, but it has got some noise or some kind of distortion. So what we are going to do now is we will just plot the histogram of this distorted image. So imhist of capital I, the distorted image. Then you can see that rather than having three different peak values at 0 or 1 in the middle gray level or at some value 225 or something, it is getting several values rather than three values, but those values are having some pattern, because a single value is added with some values that has got a pattern. So if you look at this distribution of pixel, it's kind of look like a Gaussian noise. So you can actually interpret from the image that this is the image has been distorted with a noise which has a Gaussian noise model. Okay. Going back to some examples in the presentation, and here I have shown three different examples. We have a image, this is actually distorted with a Gaussian noise, and this one is distorted with a Rayleigh noise, and this one is distorted with a gamma noise. So here you can see that the difference between Rayleigh and gamma, there is a small difference in its shape. And on three other examples, first one is the exponential noise, then uniform noise, then we have the salt and pepper noise. So in the exponential noise, the noise values are decreasing from the 0 value, and here we have the portion corresponding to the gray area. Now previously we just had a gray pixel only. In that case we had only one value here, but all those values are distorted with some noise which has a exponential distribution, and here the black values distorted with the exponential noise. And here we have an image which is distorted with uniform noise, because previously we had only three distinct levels: white, then gray, then black, but all those values are distorted with several values which has got a uniform distribution. So there is no specific no value which has got a specific weightage or specific importance. And this is another one. We have three different pixels intensities, just like in the previous case. We have a white, then a gray, then a black. And in the case of salt and pepper noise, we will have either a value which is equal to the black value. Okay, let me call it as A, another value, or a white value B. So what happens is this is actually distorted, which that is some pixels are completely gone black or some pixels are completely gone white. So previously we had some contribution for the 0 value, and some contribution for the gray value, and some contribution for the white value. The value was around 255. But now you can see that we had got one more contribution, and this contribution comes from the fact that there are several pixels now changed to completely white, which means that those values has become 255. And we have seen that some the contribution of the value 0 has increased a little bit, because some values in the gray region and some values in the some pixels in the white region have completely gone black. So those values will be contributing more to the black pixels in the histogram after distortion. Okay. So this is the idea of different noise models. I hope it is clear, and thank you very much.